Alright, let's get started with Lesson 10, Nuclear Charge. For the remainder of this unit, we are going to be focusing on applying quantum mechanics and Coulomb's law to periodic principles, as we will see in the following lessons. In this lesson, we are going to focus on the nuclear charge and what it is, and how the nuclear charge affects the valence electrons in that valence electron shell. Alright, first of all, what is the nuclear charge? Now, if you recall from Unit 1, Z, the letter Z represents the number of protons in the nucleus, or the atomic number. And if we write out the isotope symbol, remember X represents the symbol, the isotope, and then A is the mass number, and then Z is the atomic number, or the number of protons. Alright? So by definition, the atomic number is the number of protons in the nucleus, but so is the nuclear charge. However, the nuclear charge has more meaning to us, because the nuclear charge relates the attractive force between the nucleus and the electrons in electron shells, specifically the valence electrons. Now, remember, the valence electrons are the most important electrons in the atom. The valence electrons are going to determine the chemical properties of the atom. And the nuclear charge, or the force of attraction between the nucleus and those valence electrons, are going to have an impact on the overall properties of the atom. So what we find is here, the higher the nuclear charge increases the nuclear electron attractions, and thus lowers the sublevel energy that stabilizes the atom. So all we're saying is basically you have the nucleus. We'll say this is the nucleus, and it has a certain number of protons, and the electrons out here in the valence shell, there is an attraction between the nucleus and those electrons, and the strength of that attraction is determined really by Coulomb's law. And so you should write that in your notes. Coulomb's law governs the attraction of the nucleus to the valence electrons. Alright, now here we have a model of the atom. We have the nucleus, of course, right here, and we have electrons in the inner shells, and we have an outer electron shell. So this is out here, the outer shell is the valence shell, where the valence electrons are located. And so if we haven't made that clear, just remember that the valence electrons are in the outer electron shells, and that electron shell is known as the valence shell. All the other electrons that are not valence electrons are known as core electrons. Alright? So hopefully that's clear. So this model has some core electrons, and actually there are 3 electrons that are being represented as core. So So this is an electron in the core, this is a core electron, and this is a core electron. And the other electrons out here, valence electron, okay? I think you get the idea. Now, what we're going to focus on is the nuclear charge is again, the number of protons that are in the nucleus. And as we know from Coulomb's law, the higher the nuclear charge, in other words, the more protons in the nucleus, there's a greater magnitude of charge that's placed on those protons as a whole, and therefore there's going to be a greater attraction from the nucleus to the valence electrons. We also know from Coulomb's law that if the electrons get further from the nucleus, the attraction between the nucleus and the electrons should diminish, should go down. Alright? And we see that attraction represented here by these arrows. But we also have some repulsions going on. Now the repulsions are occurring between the core electrons and the valence electrons. Remember that the electrons are negatively charged, so negative charged particles are going to repel each other. They're not going to like each other very much. And that's going to have a dramatic impact on the attraction between the nucleus and the valence electrons, is those repulsion between the core electrons and the valence shell. As a result of the effects of the core electrons repelling the valence electrons, we have a concept known as shielding. Now, shielding, by definition, is thought of that in multiple electrons, atoms, each electron feels not only the attraction to the nucleus, but also repulsions from other electrons. Repulsions, then, are going to counteract the nuclear attraction somewhat, making it easier to remove an electron. So let me kind of clarify this for a minute. When we're talking about removing electrons, we're talking about removing electrons from the outer valence shell. And the stronger the attraction of the nucleus to the valence electrons, the harder it is for us to remove an electron. Right? However, because of the core electrons causing the repulsions on the valence electrons, the nucleus cannot hold on to the valence electrons as easily as they would if those core electrons were not there. So, in other words, let's look at it this way. If I remove these three core electrons in this diagram, it would be harder for the valence electron, this valence electron here, to be removed from the atom. All right? But because these core electrons exist, the electrons in the valence shell have an easier time being removed. The nucleus cannot hold on to them as tightly. All right? Now, the core electrons then are shielding the valence electrons. Kind of think of it this way. The core electrons are acting like a force field, a shielding effect that keeps the nucleus from fully reaching out and holding tightly to the valence electrons. Now, if we remove those core electrons, then the nucleus would be able to hold on to that valence electron a lot tighter, and it would be harder for the electron to actually be removed. All right? And so this concept is known as shielding, or shielding effect. All right? And by the way, the more core electrons there are, the stronger the shielding effect will be, and the easier it is to remove an electron from the valence shell, and the harder it is for the nucleus to hold on to it. All right, now, new terminology then. Effective nuclear charge. Because of the shielding effect, the nuclear charge will really be known as the effective nuclear charge. The effective nuclear charge is the nucleus valence electron attractions that actually occur as a result of the electron shielding effect. All right? So I really want to make sure that you understand this effective nuclear charge. Okay? So let's relook at this really quickly before we go on. The nucleus is attracted to the valence electrons. I think you understand that. And it's the magnitude of attraction really depends upon Coulomb's law. So the more protons in the nucleus, the stronger the attraction between the nucleus and the valence electrons. Also, the closer the valence electrons are to the nucleus, the stronger the attraction forces, all based on Coulomb's law. Now, where shielding comes into place is, again, the core electrons shield the valence electrons from the nucleus. That means that the nucleus has a harder time attracting to the valence electrons. They can't hold on to them as tightly. If we remove the core electrons, the shielding effect goes away, and the nucleus is now able to hold on to those valence electrons with a tighter grip. All right? So I hope you understand that. So with the shielding effect, the effective nuclear charge is what is really the force of attraction between the nucleus and the valence electron shell. All right, so let's look at these two atoms here using a simple Bohr model. The atom on the left has 6 protons and 6 neutrons. It also has 6 electrons. The atom on the right has 8 protons and 8 neutrons, and also has 6 electrons. Okay. Now let's do some thought process here. Okay. So we're going to compare electron 1 and electron 2 as a review a little bit here of Coulomb's law. Okay. Now the nuclear charge on this atom is going to be 6 protons. All right. And those 6 protons are attracting to electron 1, which is a valence electron, as well as to electron 2, which is a core electron. Now, according to Coulomb's law, because electron 1 is further from the nucleus, then electron 1 should have a lot less attractiveness to the nucleus than electron 2, since electron 2 is closer to the nucleus. And I think you understand that. The question is, though, the effective nuclear charge. Does these core electrons, like electron 2 and the one over here, are they going to have an effect on the overall attraction of these 6 protons to this one valence electron? And the answer is yes. Those core electrons are going to shield electron 1 from the nucleus. So the nucleus cannot pull or hold on to electron 1 as tightly if we removed those 2 core electrons. All right? All right, let me erase this. Now, let's do a comparison here of electron 1 and electron 4. Okay? Now, out of these 2 electrons, do they experience the same shielding effect? And the answer is pretty close. And that is because they both contain 2 core electrons. Right? However, will these 2 electrons, electron 1 and electron 4, have the same attractiveness to the nucleus? And the answer should be no. Which one is going to have a greater attraction to the nucleus? If you said electron 4, you would be correct. The reason why is because the nuclear charge on this atom is 8 versus 6. Since there's a higher magnitude of positive charge, according to Coulomb's law, there should be a greater attraction between electron 4 and the nucleus than there is for electron 1 in the nucleus. All right? So it's these kind of thought processes that we kind of got to look at, okay? And this interaction between the protons in the nucleus and the valence electrons in that valence shell are going to have dramatic influences on the properties of these elements. So we need to walk away understanding the effective nuclear charge, shielding, and how all of that affects with Coulomb's law on these valence electrons. Okay? So this is it for this particular lecture video. Please take good notes. Prepare for a quiz that we will have over this. All right, and that is it for now.